I'll try to tell you a little bit about quantum technologies today, something about computing, maybe communication and sensing. Um, a quick word about myself. I'm a physics professor at the Technion. I'm an experimentalist. I'm doing experiments with ultra cold atoms, and I'll tell you a little bit later on how they merge in this field of quantum technologies. And in addition, I am the co-founder of a new startup company called Q Factor, which is working in the field of quantum computation, again with cold neutral atoms. And it's all, of course, coming out from the Technion. So I'm very happy to be here in this alumni um meeting. So what are we going to talk today? I'm going to give you a really brief introduction to quantum mechanics. I'm not going to assume you are a physicist or you know physics. Um, we'll talk a little bit about what gave rise to quantum mechanics and what properties in quantum mechanics are really important for quantum technologies. Then I'm going to tell you a little bit about applications, what things you can actually use in quantum mechanics to do things you cannot do classically. And then we're going to talk a little bit about technological implementations, how people actually build things that do this stuff in real life. And in the end, I'm going to tell you a little bit focusing on the technology that I'm an expert on, which is neutral atoms and how one can do quantum computation with neutral atoms. We'll talk a little bit about what's actually quantum computation. Um, that's the menu for today. Um, but I'll start with an image, and I want you to take a moment to stare at it and ask yourself if you know what this image is actually. Um, maybe you know, maybe you don't, but this is actually the first computer that was built in the United States, and it was built in, let's see why, just 1 second, if you don't mind. So this is the first computer that was built in the United States. It was built in 1945, and it was built to do basic calculations that up to that date was done manually. And I want you to take a minute and compare what 80 years of technological progress have done to classical computation. So the ENIAC, it was a computer built at a cost, adjusted cost of $7.5 million, and just compare it to the some laptop you buy today in few grands. It was built out of 18,000 vacuum tubes, and again, you can compare it to the number of computing elements you have today in each, not even a computer, even in your cellular phone. So that's an amazing number. The weight was 30 ton. And now a computer of 2 kilograms is considered heavy. The footprint is essentially a whole room. So the things you see there are just cabinets full of vacuum tubes. And also the electrical consumption was amazingly high. In fact, people said that when the computer was operating, the village nearby was the lights was flickering because the electrical consumption was so high. And I think maybe the most impressive number to compare is actually the number of instructions this computer can do in 1 second, which was around 5,000. Again, an amazingly high number for that point, but compare it to what your laptop computer can do, which is about it's about 200 billion operations, instructions per second. And so the main message I want to convey is that it's really hard to imagine how 8 years of progress, what did they do? I mean, if you would throw yourself to 1945, it would be very hard for you to imagine that. And I want you to keep that in mind during my lecture because some of what I'm going to show you maybe will sound like science fiction. So just open your mind to this notion that maybe in 8 years all of that would be cramped into some quantum laptop on your table. And let's start with the introduction to quantum mechanics. So sometimes we are talking about the first quantum revolution starting at the early 20th century. And it's really all about science starting to look and shift the attention from macroscopic phenomena to the processes that live in the atomic scale. And those gentlemen whose pictures you see on your screen are really the ones who are responsible for this revolution. You see Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, and they are only some of the heroes. Um, but they had a particularly important role in this revolution. And I want just to tell you about few landmarks in this revolution. So maybe the first one is what is called the black body radiation, and it takes us to observations done already before the 20th century. And it's essentially something you see every time when you see a very hot material like metal or even hot lava and you see it glowing in red. We know that things glow in light because they are very hot. And the spectra of these materials depends on the temperature and not so much on the material itself. I mean, if you take iron or aluminum at the same temperature, they are going to have more or less the same spectra. And so the question was, how do you explain this spectra? And the naive classical explanation, taking into account classical statistical claims, had a problem at very short wavelength, something that was called the ultraviolet catastrophe. It could not actually explain why the energy looks like that, why the spectra looks like that. And then Planck came and said, well, maybe the energy is actually quantized. Maybe it's not something that comes in every size. It actually quantized the particular quanta, and he invented a constant called Planck constant today. And it turns out that this sole assumption explained the whole spectra. So at that point, people did not know why, but it already was indicative that this is plausible explanation of how things behave at a very small scale. Then another very important effect is the photoelectric effect in 1905. Einstein explained the phenomena in which people observed that when you shine photons on a material and you look on the current, on the electrons that emitted from the material, it doesn't look like they depend on the energy, does not look like it depend on the frequency. Sorry, it doesn't look like it depends on the intensity, but actually on the frequency. And again, Einstein saw and explained that if you just assume that the light consists of quantas, of photons, it's enough to explain this phenomena, again, using the same idea that the energy is given by some constant, again, h times the frequency of the photon. So these were already two indications. Um, Funny enough, out of the many, many, many amazing contributions, Einstein got the Nobel Prize actually on this discovery. And then we jump a little bit forward in time. Bohr's atomic model is very important contribution where Niels Bohr explain the spectra coming out of the hydrogen atom. So people observe that when they excite an atom, like the hydrogen, for example, light does not come in all frequencies. It actually comes in discrete frequencies. And again, to explain it, you need to show that the energy of the electron in the atom is quantized. It cannot be anything. It's only some discrete values, and then everything falls into place. And again, the transitions between these two energy levels emits photons in discrete energy, exactly like we discussed before. And the last super important experiment, and again, there were many, I'm just choosing, let's say, key key experiments. This is called the Davison-Germer experiment, and it showed that when you take electrons and you scatter them on a material, in this case nickel, they scatter as if they were waves. So people knew that if they take light and they scatter off some grating, it shows very discrete peaks in the scattering, in the far field of the scattering. It was highly surprising to find that electrons behave the same way. So in effect, what it shows that electrons, in a sense, behave the same way like photons, and it really shows that there is a duality between the nature of the particle. It's not really just a point particle, but a particle can be also described as a wave. And this duality between wave and particle is really what gave birth to the whole quantum theory. And we are going to talk in most of the lecture today about the second quantum revolution, but it's important to already say that there was first quantum revolution, technological revolution, where the discovery of these properties gave rise to many technologies, and in this cartoon you can see some of them. And just to mention a few, the LED, the light emitting diode, something that you use today actually in most of our lighting and definitely in most of the compact lighting. Semiconductors. Um, you see in 1947, and lasers were invented in 1960s. Solar panels in 1954, and MRI and other medical devices in 1946. So you see, all of them actually use um, several of the properties that I just described. um, you could focus and say that the technological revolution coming from the first wave of experiments is actually using the quantization. So exactly the fact that energy and other physical properties come in discrete quanta and cannot assume any value. When you combine it with the fact that you have periodic potential, like in solid, you get energy bands, and this is yet another important feature that is used, for example, in semiconductors. And another important property is the spin that was discovered. It's a property of an electron. It's like a small arrow that is inherent to electrons and other particles. And so maybe you can already see that in all these applications, what you are actually using is the property of a single quantum particle. Like you take an electron and you manipulate its spin, or you let it behave in some way in a band in a solid. And so these are the properties that people use, and it takes us immediately to the second quantum revolution. The quantum uh, properties, they don't only stop at this quantization. They actually have three more points which I want to stress, and these are the idea of superposition, entanglement, and tunneling. So let's unpack for a second what each of these is actually. So superposition, when we say in quantum mechanics superposition, we actually mean that the quantum system can exist in multiple states simultaneously, and until it is measured. Now, it doesn't mean that you should imagine, for example, an electron in two positions. You should have in your mind something which is like a wave that is distributing in space in many places, and this wave in quantum mechanics describes the probability to find a particle in some position. So some people prefer to treat it not as a particle being in many places, but actually how probabilities are treated in quantum mechanics. So, but superposition means a system can actually be in multiple states simultaneously, something which is classically forbidden. The next thing is entanglement. What is entanglement? And I'll explain it even more a little bit later. So entanglement is the property that particles can be in exhibit correlations. For example, you can find a particle here and a second particle there, but not in any other configuration. So these are correlations between particles that cannot be explained by classical physics. And again, I'll give you an example in a short while. And tunneling is the effect that particles can actually go through barriers which they wouldn't be able to do classically. And these are the main properties in the second quantum revolution that enabled the applications we are going to discuss today and the technologies. So let's get a little bit deeper into these three ideas. So what is a superposition? So in quantum mechanics, we describe the state, we call it a quantum state, and we say it can be in a combination of multiple possible states simultaneously. And when a measurement is done, for example, if I have an electron, it can be either here or here, and when I measure it, it will collapse into one of these single definite states. Um, and this happens only when the system is measured. Before it is measured, you can think of the electron as having probability to be here and here, but it's not a classical probability. It's a quantum probability in the sense that it's living at the same time in two of these positions. And if you want to know what is the actual probability to measure something, then you have to take the square of this probability amplitude, which we call this quantum or wave function. And so the way we usually write it is in this very funny notation. So for example, here you see we wrote two position of a spin, let's say, and these alpha and beta, they give us the probability. If we take them square, then it will give us the probability to be in the up state, for example, and beta square will give us the probability to be in the down state. But before we did the measurement, this particle is in a superposition in these two states. And it brings us to a very important definition that we are going to do at this point. And this is what is a qubit. So probably you heard about the idea of a qubit. And a qubit is a shortcut to a quantum bit. And it's really the fundamental unit information in quantum computing and also in quantum information. And unlike a classical bit, which can either be in 0 or 1, a qubit, because we just discussed the idea of a superposition, a qubit can be in some state which is a combination of 0 and 1. So we sometimes depict it on a sphere, which we call the Bloch sphere. It's just a representation of the qubit, but the idea is really that every point on the sphere is one of those superpositions possible for this qubit. So you see that the classical bit actually only lives on the south and north pole of this sphere, while the quantum bit, the qubit, lives on all position in this sphere. So it's a much larger space. Um, and on this sphere, I can define all kinds of bases. For example, the natural basis is the computational basis, 0 and 1, which I just described. But I can also take another basis. For example, the one which we sometimes call plus minus, and this is the basis which live on the equatorial plane. And it's just defined by this definition of 0 plus 1 or 0 minus 1. And it's just another basis that you can work in, and sometimes it's more convenient. And we'll get back to it because it's going to be important in the discussion we're going to do next. Now, just to already comment here about physical implementations, many quantum systems can offer you two levels, and they can behave like a fair qubit. So you can think about photons, atoms, or ions. You can think about electrons. We discussed about spin, so spin is a good qubit. Superconducting circuits, we're going to discuss it a little bit, and many other systems. All we need to do is essentially choose two levels, which we know already are quantized, and once we identify them, we can define the qubit in these two in two-dimensional subspace. Now let's talk about quantum entanglement, and that's a little bit more complicated idea to explain, and I'll try to do it without being too mathematical, and we'll see how it goes. I did bring this quote from Einstein that called it a spooky action at a distance. And it's spooky because, as I said already, quantum entanglement are long distance correlations between particles. And so it's kind of weird that you do something in one position and it immediately affects the state of the atom in another position. But that's essentially what happens in quantum mechanics. So let's see how it works. So imagine a shared quantum state, for example, of two particles. It can be of more, but let's keep it simple for now. And if I now measure one particle and I find, for example, the spin result, it can be either up or down, it immediately affects the outcome of measuring the other particle, although they may be super far away from each other, maybe in another galaxy. So it's it's clear that they cannot exchange information, and yet their state is somehow linked together or entangled. This is why we call it entanglement. It's because the state of one is going to affect the state of another. So, for example, if I do a measurement and find the spin down here, I will find the other particle in spin down and the other way around. And this is correlations we cannot explain classically. And so let's imagine a theoretical, for now, experiment in which we send two photons, for example, to Alice and Bob, which are observers very far away. And these photons, they arrive and do a measurement of polarization. So a photon can have polarization, which is just the direction where the electric field is going to point. So it can be either, let's say, up or at 90 degrees, or horizontal or vertical. And they choose and they measure and in this basis, and each of them writes the measurement results, and afterwards they compare, and they see that every time one of them measured zero, let's say Bob measured zero, Alice measured one, and whenever Bob measured one, Alice measured zero. So they see perfect correlation between their measurement. And of course, this can be explained by just the quantum wave function that I just wrote here. You see, it's written as a superposition, written like 0, 1, and 1 of the second particle, or 1 of the first particle and 0 of the second particle. So if you look on this wave function and you say, let's say I measured 0 for the first one, immediately you see that you get 1 for the second particle. But in fact, there is an easier explanation to this correlation. You could think maybe whoever prepared these photons just prepared them in a correlated way, right? I mean, I can prepare photons in correlated way and then send them, and this would be just a classical correlation. It's like you take a pair of socks out of your drawer. Of course, they are correlated. They will mostly be in the same color. You wouldn't call it a quantum effect. How do you know to distinguish between just a classical correlation and quantum correlation? So that's an important question, and it's a subtle point. The way to show you is actually to go and change the basis. So if now I tell Alice and Bob that they can actually measure in another basis, which will be the plus and minus, okay? And so what would happen now is they would still find perfect correlation in these new bases. Namely, if Bob finds in the plus, minus, Alice will find it in the minus, and the vice versa. And why is it? Well, I leave it as a mathematical exercise for you, but I'll just tell you the result. If you take the wave function that I just wrote, which is written like 0, 1, minus 1, 0, and you now write it in a new basis, you will find, and it's a one line of calculation, that it's essentially looks the same. It's just plus, minus, 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 plus. You see it's written. Maybe it's easier to just read it than spell it out. And so the perfect correlation are preserved. Oops, sorry. The perfect correlation are preserved even in this. No, why did it do that? Sorry, apologize. The perfect correlations are preserved in the even in these rotated bases. And a very famous scientist who understood how to quantify it, his name was John Stuart Bell. And Bell in 1964 showed that actually you can write an expression, this E, are a measure of correlations between measurements, and A and B are just the basis on which you measure. So A1 would be like the horizontal basis, and B1 would be horizontal. So A1 would be the basis in which Alice measure, and B1 would be the basis in which Bob is measuring. And you can choose sets of bases, and whatever you choose, classically speaking, the correlations would never exceed 2. This is the value of this expression, and he proved it, and in all classical theories, this must be satisfied. However, when you write the quantum mechanical prediction, it actually shows that this expression is 2 square root of 2. So it's going to be larger by a large factor of 1.4. And what's really impressive is the experiments that followed. So these three gentlemen, Alana Spee, John Clauser, and Anton Zeilinger, they did a series of measurements with photons emitted from an atom. So the experiment is really very close in nature to the Gedanken experiment. The photons are going to be emitted from the source, from the atom, but they are always going to be correlated in some property, for example, the polarization. But you don't really know the properties, so they are going to be in entangled state. And so they did experiments and they measured this correlation and showed that it adheres to the quantum mechanics prediction, which proved that indeed non-local correlation exists and entanglement is really a real property of nature. And so the bottom line is that we know today that indeed quantum particles have these long range non-local correlations that are very, very weird. And just a last comment on that, some people mistakenly think that this allows you to communicate information in a velocity which is much more than the velocity of light, and this is not true. The fact that you have correlation does not mean you can actually transfer information between this observer, and you can actually show that this correlation will not break any prediction of the relativity theory. So although it's very weird to think that something you're doing here is immediately affecting the other particle, which may be in another galaxy, it does not mean that you can actually transmit information to the other galaxy, and in that sense, its causality is still it's still maintained. So entanglement is going to be very important in some of the applications I'm going to show you. And now the last thing I want to expand a little bit is the idea of tunneling. Tunneling, I already mentioned, is the property that imagine you take a ball and you bounce it off a wall. And then let's say you do it like 100 times, and once or twice out of these 100 trials, the ball just passes through the wall and continues to the other side. So that's more or less what happens in quantum mechanics. Although there is an energy barrier that forbids the particle from, classically, I mean, to pass, in quantum mechanics, there's a small probability that it will actually will pass through this barrier and we'll find it on the other side. And we explain it by exactly this duality between particle and wave, because again, we are using the idea that particles are also waves. Then a wave can actually penetrate and decay slowly into the barrier and then leak on the other side, and then it extends on the other side, and there is a finite probability then to find the particles on the other side. And again, you could think it's just um, something you would imagine or a science fiction, but this is not only, it's not science fiction, it's actually technologically very useful. And I'll give you two examples. One is a device called Josephson junction. It's a device made of a superconductor and two superconductors, and in the middle you put a very thin layer of insulator. So it's like a sandwich of an insulator and a perfect conductor. And one can show that because of this effect, the tunneling, uh, quantum particles, electrons, pairs of electrons, in fact, can go from one side, from one superconductor to the other in a very particular way. And this device is extremely important in many applications, ranging measurements of magnetic fields and also generation of qubits in superconducting circuits. And so I'll get back to it in a short while. And another application I want to tell you about is a device called scanning tunneling microscope, or STM in short. And it's a device where you take a needle, a very, very thin tip with a very sharp tip, and you get very close to a surface with this tip and you scan the surface. And then what you're doing is you're putting some voltage between the tip and the surface. And because there is tunneling, there is a finite probability that the electrons will go from the tip to the surface. Although, again, classically, it is forbidden. And what you're actually doing is you're measuring these tunneling current. And this tunneling current is super sensitive to the distance between the surface and the tip. So if the tip goes and just scans, it essentially this current actually shows you the topography of the surface. And so you can reconstruct the structure of the surface and see even atoms, individual atoms using this technique. And it's a super powerful tool in physical characterization of surfaces. And now when we have these ideas at hand, I want to kind of get more into the technology side of these properties. And I'm going to discuss three main technologies, three pillars. And this is the quantum sensing and communication and quantum computing. Um, so um, what each of them is going to be. Quantum sensing is really just to do precision measurements that are beyond any classical ability. And I'll show you examples of how we can measure time and forces using these systems. Quantum communication is all about your ability to communicate information securely. So I would say that the main property of quantum communication is really about secure and security, which is guaranteed in a very basic level by quantum mechanics. And then quantum computing is going to be all about the ability to compute things you cannot compute classically. So doing computation, which in a sense is much more powerful than classical computation. And here I'll show you some examples of algorithms coming from cryptography, search, etc. So let's start with quantum sensing. So the first example I want to tell you about is how you measure time. This is the idea of an atomic clock. So an atomic clock is really just the idea that if you take an atom, and we already discussed the idea that energy in an atom is coming in a discrete level, so discrete states, and that if you have and you have an electron that goes from transition between these two states, it's going to emit a photon at a very well-defined frequency. And then you can use this frequency as a clock. If you think about it, the pendulum clock, just what you do is you measure some frequency very accurately. And you can do exactly the same with photons. I mean, if you take the photons and you know that they always emitted the same frequency, then you can use this frequency to measure time. And that's actually how we define today time. We actually define the second today according to a transition in a cesium atom. So we look on a cesium atom and we look at a particular transition in the hyperfine ground manifold, and we define the second as the number of oscillations between these two states. In fact, it's like 9 billion something oscillations. And these are the most accurate clock today that we have. So the most exciting front in measuring time is actually atoms that are being held in optical lattices. Optical lattices are traps made of light. You take lasers essentially and you let them interfere and create a fabric of light. And in this fabric you can actually hold and trap atoms. All this is done in a vacuum chamber. Of course, the atoms need not be disturbed by the external environment, and then you can probe them and extract the transition you are going to probe. Because all the atoms are the same, it means all the clocks are the same. So it assures like utmost accuracy and reproducibility. It doesn't matter where you are. If you take the same cesium atom, it's always going to have the same transition frequency. So all your clocks are by definition at the same. You need some kind of electromagnetic radiation to probe this system. It's either microwave or lasers. This is how we probe this system. And when we hit exactly the resonance transition, we know that our pendulum is exactly on the right frequency. And this is how we tweak our clock. And just to give you an idea, today's most advanced optical atomic clocks are so accurate that they are not going to miss even 1 second over 30 billion years. So the level of accuracy is just mind-boggling. And one could wonder why would we need such an accurate clocks. So there are many reasons, but one reason we as physicists want very accurate clocks because it allows us to measure other phenomena very accurately. So it allows us to probe fundamental laws of nature in a very precise way. So this is an example of quantum sensing, which is not possible in any classical sense. Let me tell you one more example of quantum sensing, and it will be atomic interferometer. So the idea in general of interferometry, which comes from light, from photons, is the idea that you can take a photon, split the wave into two, let them propagate different paths, and then recombine it and measure the phase difference along these two paths. And this is the photonic interferometer, but we are going to discuss now atomic interferometers because quantum mechanics tells us that atoms are both particles and waves. So it means we can actually also split atoms and recombine them, and by doing so, being very sensitive to effects which apply to massive particles. So this is exactly the idea of a matter wave interferometer or atomic interferometer. It's just a device that exploits this nature, this wave nature of atoms. And the way it works is you usually you take an atom, you split it in momentum space, which is in another way to say that you split the atom into two parts, one moving in some velocity and another part which move in another velocity. So these two parts just slowly separate, as you see here on the picture on the right. And then these two parts can actually do a closed trajectory and recombined. And when they recombined, you can measure the phase that these two massive wave packets underwent. And this phase is sensitive to both forces and acceleration happening during this loop. So these type of devices are super sensitive in measuring forces like gravitational forces, for example, and are excellent in also measuring acceleration. If you take them as an accelerometer, for example, they can measure very accurately the acceleration. So that's another example of how to use the quantum properties to do unique sensing. Good. Now let's move to talk about quantum communication. So again, quantum communication, it's all about uh, communicating information in a way that is completely secured. And so why would quantum mechanics actually give you this ability? So what quantum mechanics give you is the ability to exchange a cryptographic key in a totally secure way. So a cryptographic key is a very pompostic way to say just to share a random number, a random string of bits between two particles, Alice and Bob, let's say. So if I want to securely transfer a message. If I have a random key and you have the same random key, we can do that. We can encrypt using both keys and then decrypt it, and it's completely secure. But how do we do that? How do we exchange? How do we create the situation that both Alice and Bob have this the same secure key, and nobody else can actually eavesdrop and know it? And the idea is that quantum mechanics show us that any eavesdropper, any trying to disturb the quantum particle leaves a trace on the quantum particle. In fact, we have a theorem that is a very important one in quantum mechanics, and it's called the non-cloning theorem. The non-cloning theorem, which is just a direct manifestation of the equations of quantum mechanics. It says that an unknown quantum states cannot be copied. So if you imagine like a Xerox machine that you take a quantum state and you put it there and you have then two copies of the same state, then the non-cloning theorem says you cannot do that. And that's very important because it means that you can use the non-cloning theorem to generate this secure key between the two parties that want to communicate. So let me show you an example of the most simplest example. It's a protocol called the BB84, and it goes something like that. Alice wants to communicate a message to Bob, so she takes a random bit of, she takes single photons, and the goal now, remember, is to generate a random bit, a random string of classical bits. So what Alice is doing is she's going to encode the bits in the polarization of the photon, of the qubit, and she can decide randomly whether she encode it in the basis 0, 1, or whether she's going to encode it in the basis of plus and minus, which is rotated in 45 degrees. And she decides totally random, and then she sends the photon. And what Bob is going to do, Bob is going to randomly choose also the measurement basis, either in the basis of 0, 1 or in the basis of plus minus. Now, if Bob accidentally chose exactly the same polarization that Alice used, then they are going to have the same information. If Alice encoded 0, Bob is going to measure 0 or 1 exactly. Of course, if they measure in the wrong basis, it's going to be non-correlated. Now, what Alice and Bob are going to do, they're going to take part of this message and publicly communicate between them and say only the bases now, not the bits, and say this is Alice is going to tell Bob this is what the bases I actually used, and Bob is going to tell her, well, this is what I measured in this basis, and then they're going to compare. And the non-cloning theorem says that if somebody tries to eavesdrop, they are going to see that they don't have perfect correlation. So if they find that they have perfect correlation in this subset, it means that nobody eavesdropped, and they can treat the rest of the bit stream as completely secure and use it for the secure communication. So they're going to discard this part of the one they actually shared, but all the rest of the bit stream is going to be useful if they find that nobody eavesdropped. And so this is essentially how you do secure communication. And this is not just a theoretical idea. There are already companies working in the field and producing devices like you see here, for example, on your left, that actually implement these kinds of quantum key distribution as a way to have a completely um, secure communication. And just a quick kind of a comment on the challenges of doing that. I would say the main challenge is actually doing that for long range, extending the range. And this is because photons are lost in optical fibers. So most of the communication we do and today, like internet today, is done in optical fibers, but photons are lost in fibers. They are either absorbed or scattered as they propagate through the optical fibers. And so the question is, how do you go beyond the practical limit, let's say, of 100 or 150 kilometers? We already know we cannot just clone a state. So how would you then do the communication more redundant? This is the challenge essentially. And there are two main solution people try to develop, technologically speaking. One is something called quantum repeater. It's essentially a way to extend the usability of entangled photons beyond by swapping them in nodes and then just putting those repeaters along the way. And another way, which is in my opinion even more promising, is using satellites. So essentially, if you think about a satellite, it can communicate with two ground bases, and then it can be the facilitator of exchanging these secret keys. And if you think it's a science fiction, then the Chinese already have such an satellite operating, and they published it and demonstrated it. So this is definitely a viable technology that I would say big and powerful countries are using already today. Okay, next we are going to talk about quantum computing. And let me first explain briefly what's quantum computer. So a quantum computer starts by taking qubits. We already know that qubits are quantum creatures that can be in 0, 1, or superposition of them. And we start by initialize them then, let's say to the state 0. Then after that, we are going to apply gates. Gates can be, we're going to talk about it in a second, but they are going to be some manipulation of either 1 or 2 qubits. And then in the end, we are going to measure the qubits. These red boxes you see. These are measurements are going to tell us something about the state of the qubits. And once we measure, the state collapses, and then hopefully from this measurement, we gain information about the problem we are really interested about. Um, an important point in doing this type of quantum circuits is that because quantum states are fragile, they very easily get ruined by classical intervention, then we need some way of actually protecting them, and that's the idea of quantum error correction, which is super important in actual implementations of quantum computation. How do we discuss when we write it? So again, I'm doing this short mathematical interlude just to be a little bit more concrete. So I hope most of you maybe saw the idea of vectors in maybe linear algebra, but if not, don't worry, it's going to pass quickly. So I write the state of the qubit as a vector. You can see it here. And then again, a general state of the qubit can be written again as a vector alpha beta. And again, I just remind you something I already said. If you want to know what's the probability to be in 0, it's alpha square, and beta is and 1 is beta square. And now, what's a quantum gate? It's kind of similar to classical gates, which all of us have in our devices, like in our computer, like AND and or XOR. So quantum gates are just a manipulation, very similar manipulation. But unlike classical gates, these are reversible manipulation of the qubits, of single qubits. And usually they are described as unitary transformation. So this is just, again, meaning they are reversible. And here is an example of one such gate. This is called the Hadamard gate. And if you ask yourself what this Hadamard gate is doing, then it's actually fairly easy. If you take a qubit in state 0, and you apply the Hadamard gate on this qubit, what it's going to give you in return is just a superposition of 0 plus 1, which I remind you, it is just the plus state. So Hadamard gate is just a rotation that takes you from 0 to plus, let's say, and from 1 to minus. So it's a rotation in the Bloch sphere. Okay, if you remember again this depiction of the qubit in the Bloch sphere, these gates are just rotation in this Bloch sphere. And they are very general. They can be any type of rotation, but most generally, these are just rotation in Bloch sphere. Here are a couple of important gates. For example, there are some gates we call Pauli gate or X gate, and they are essentially very similar to the NOT gate we have classically. So if you have 0, it's going to give you 1, and if you give it the qubit 1, it's going to give you back 0, and it flips. Essentially, it flips the state of the qubit. We have phase gates, which are going to leave intact the qubit 0, but going to give a phase of I phi to the qubit 1. And then a very important class of qubits are those of gates, sorry, are those that act on 2 qubits. For example, a controlled NOT gate is a gate that is going to flip the second qubit depending on the state of the first qubit. So I have a control qubit and then a target qubit, and if the control is 0, nothing is going to happen to the target qubit. But if the control is 1, I'm going to flip the state of the second qubit. And very similarly, I can also define a phase gate, which is a controlled phase gate. Only if the two qubits are in 1, 1, I'm going to have a phase given to this state. Now, two qubit gates are essential to generate entanglement, which, as I'm going to show you, is really at the heart of quantum computation. But before that, you might say, wow, I mean, I can imagine you talk about rotation, so I can imagine any kind of rotation. So how am I going to build a quantum computer? And if I need to generate all these immense types of gates? And the answer is you don't have to. You can actually implement a very small set of gates, which are called universal sets, that if you know to implement them, then you're good to go and you can actually create any kind of other gate you want um, to arbitrary good accuracy. And I'm going to show you two examples. So here are two sets that are universal. So maybe the most simplest set is the one which include the two qubit gate C naught, which I already explained, the Hadamard gate, and a phase gate. This S is the phase gate giving a pi over 4 phase. So you see, only by implementing these three types of gates, if you know to do that, you already can essentially implement any algorithm, any quantum algorithm. Let's talk about quantum circuits. So these are just graphical representation. For example, this is how we would depict a Pauli gate on one qubit. These lines are just what happens to a qubit, right? So each line is a qubit. If I need to apply a qubit, a gate between two qubits, like this C naught, then I would connect these two lines. And if I need to do a measurement, then this is how I would depict it. And let's take like a small exercise. Let's imagine I start with a very simple state of two qubits. Each of them is starting at the state 0. So that's what you see on the left side. And now what this circuit is saying is apply a Hadamard on the first qubit, and then afterwards apply a controlled knot between the two qubits. And I want to show you that this very simple circuit creates an entangled state. By the way, this state is called the Bell state. And it's a very special state that has a complete correlation between the two qubits, right? If one is 0, then the other one is 0 as well, and the other way around with 1. And so let's go slowly and see how does it work. So we start with 0, 0. This is the initial state. And then the Hadamard is going to be applied only on the first qubit. So it's going to rotate it to the plus, the 0 plus 1, you see. This is still not an entangled state. I can separate and discuss the state of these two qubits in a completely separated way. I mean, they are separate, they are still independent. Then I'm going to apply the control knot, and the control knot is now, you see, the 0, 0 stays exactly untucked in the control knot, but the 0, 1 part of the wave function is changing to 1, 1 because I already told you that the control, which is the first qubit, if it's 1, then you're going to flip the second qubit from 0 to 1, which is what is happening here. So the result is the state 0, 0 plus 1, 1, which is an entangled state of two qubits. So these examples show you that by only applying these two gates, and in particular the C naught gate, you created a fully entangled state of something that was initially completely disentangled. So this is showing you the power of these types of gates. Now, why quantum computers are believed to be so powerful? I mean, where does the speed up comes from, right? So here is how it works. If you start with many, many qubits, all in the zero state, and you now applied Hadamard to all of them separately, so it's like I'm going to rotate each of them to the 0 plus 1, and then if you just write it and you think about it for a second, maybe you can see that when you open all these parentheses, you're going to essentially get all the possible combination of these qubits. So if you choose one of these combination, it's going to be one of the possible combination of 2 to the power of n of a bit string of n qubits. But this quantum state includes actually all these combinations at once. So initially you start with all the possible initial states. And then if you want to compute a function, let's call it f, a function, some function, and you take this initial state and you calculate this function, you essentially calculate the function in parallel on all the possible initial state, but you did it in one step. So this superposition gave you a parallelism uh, in something that looks like a free lunch in a sense, and it's not. Why it's not a free lunch? It's because if you do a measurement, I mean, you would like to know this f, and you measure this wave function, you would only get one of the possible outcome. I mean, I already told you that upon a measurement, the system collapses and then you get only one of the x's. You don't probe all of the possible income. So you could say, okay, then at some point I had it mathematically speaking, but how is it actually helping me if I cannot have all of that? So the second part is actually the more important part, and it's the interference. The idea of quantum computation is really that you take this state that includes all the possible application of the function, and then you manipulate it smartly such that all the wrong answers in a way are going to interfere destructively, and then your probability to find them is going to be zero. So the trick is to build an algorithm that is going to give you a very high probability to find only the correct answer. And this gives you the speed up of you both did something in parallel, and very cleverly you somehow distilled the correct answer from all the options. So which quantum algorithms we know? I'm not going to do a complete survey, just to give you some examples. So this is an important algorithm. It's called the Grover algorithm, and it's an algorithm that allows you to search in a list. Let's say you have n items and you want to find one item. Then the quantum version of this algorithm can do that in a time which scales like square root of the number of items, while the classical algorithm scales like linearly. So this is, I mean, just imagine you have 100 elements, then instead of taking 100 time, it's going to take 10. So it can be a huge speed up here. Another example is Shor's algorithm, which can factor integers. very large integers. In fact, we don't know how to do that classically. I mean, the classical algorithms, they take exponentially long time. And because this is such an difficult uh, task to do classically, all our modern encryption is actually based on this idea. And maybe you heard about the RSA. I mean, the information you exchange on the internet is based on the idea that it's very hard to factor very large integers. But Shor's algorithm actually knows to do that in a polynomial time. So if we would have a quantum computer tomorrow morning, probably the first application of many, let's say, governmental agencies would be to break the RSA and other similar elliptical codes, etc. And that's already a big problem that the communities are kind of thinking of how to handle this post-quantum encryption challenge. And the last example of algorithms I want to mention is just quantum simulations. Quantum computers can simulate very naturally Hamiltonians and physical systems that are quantum in nature and are very hard to simulate classically. And again, here the speed up can be exponential, and this can be super important for example, all kind of material discovery, material science, chemistry, drug discovery. So these applications can benefit hugely from these types of algorithms. In quantum error correction, so very quickly, you want to, the types of error you want to prevent or protect are bit flip. Sometimes, bits will flip or phase error will happen. And you need quantum error correction because decoherence, the fact that these systems slowly become classical, is something that always exists. And so you need some kind of algorithm that will allow you to correct for these errors. But of course, the challenge is you cannot measure the actual qubits, because if you measure them, the state collapse and the measurement kills the calculation. So the trick is to do that without disturbing the actual bits that hold the data. And so many times you actually separate between qubits that are going to be what we call the data qubits and syndrome qubits. And the syndrome qubits are those that tells you whether error happened. And if you measure them, you can actually correct for errors. And I just want to mention, again, this is very interesting and a whole lecture can be done on quantum error correction. But a very important result by Dorita Aronov, she's an Israeli scientist, who proved that if you have error correction, you can actually, and you have good enough fidelity for operations above 99% more or less, then you can implement something which we call fault-tolerant quantum computing. So you can on the go correct for these errors, and it can be sustained even if you don't have perfect quantum operations. So that's really something that without it you wouldn't have even the possibility to implement quantum computation. And now I want to start closing by showing you some actual implementation. So, what are the hardware challenges when coming to realize quantum technologies? So, as I said, decoherence, you want to prevent your system from becoming classical too early. Many times you need to cool the system to low temperature, so that can be a challenge. Scalability, you want to go to very large number of qubits, and you want to do it without all your resources uh, compounding exponentially. And many times the interface between your classical control and your quantum system and the real-time error correction is highly challenging. There are also software challenges. So I told you about a couple of quantum algorithms, but we don't have a systematic way to build algorithms, quantum algorithms. And so a systematic development of algorithms for a particular problem is something still have to think how we do. And again, efficient integration of quantum and classical computing power is an open question how you do that. And so before presenting you how people actually implement, I want to present you the classes of implementation. So we talked about ideal qubits. Those are systems that have two level, and um, in real life they very hard or almost non-existent. Maybe only the electron spin, and then it's very hard to actually capture and manipulate it. So we need some kind of qubit we can actually hold to and manipulate. And there are two types, grossly speaking. There are those which I would call the natural qubits. For example, atoms, neutral atoms like rubidium 87, for example, they are natural because they are created by nature, right? But they are not two level. They have many, many energy level. So we need to isolate two of the many levels. And we need to know how to manipulate, initialize them and work with them, but otherwise they are very good qubits. And then there are man-made qubits, engineered qubits, things that look like circuits in fact, and they are very nice because they give us the engineering flexibility. But again, they are multi-level system. Again, we need to isolate two levels. But those type of qubits have variability, and we need to compensate for this variability. That is just something you cannot avoid when you produce your qubits, and it's not just God-given. Um, Let me very quickly survey the physical platforms that people are working on developing today. So superconducting qubits. These are these small circuits. I'm going to show you a picture in a second. Trapped ions. These are atoms that you ionize them and then you trap them in oscillating electric fields. Photonic qubits. You can take, we talked about photons, so people are trying to make it robust and use it. I would say that the main challenge of photonic qubits is that photons do not interact, so they need to somehow you need to mediate interaction between the photons because they don't do it naturally. And then you have neutral atoms, which are just individual atoms trapped by light, essentially, optical traps. And this is the technology that I specifically believe most in, and this is also where my particular work is done. Um, the market, when you look on companies and economically speaking, is really booming. This is just a partial list of companies involved in all types of technologies. So, for example, in superconducting qubits, you have the big giants like IBM and Google and Rigetti and others. In trapped ions, you have companies which are, some of them are already publicly traded, like IonQ or Continuum. In photons, you have also companies like PsiQuantum and Xanadu, which is also a publicly traded company. Neutral atoms is a younger field. It has several companies like Quera and Inflection and Cold Atom in atom computing, but these are, I would say, smaller companies at the moment, maybe 100, 200 employees, and not huge, still not huge investments. And there are other technologies I will not get into in sake of time. Let's maybe spend a few minutes on describing each technology. So you probably saw an image like that in some magazine discussing quantum computation. What you're actually seeing here is the inner part of a refrigerator, of a dewar. And so superconducting qubits are essentially you take a circuit. This is just an electrical circuit. But most importantly, you cool it down to millikelvin range. And in this range, the conductors become superconducting. And it also combines this element I already mentioned at the beginning, Josephson junction. And together, these circuits allows you to isolate and work with two energy levels that are produced by this circuit. So in a sense, you can think about this circuit as an oscillator that has discrete energy states, and now you take only two of them and you work with them as your qubit, and this technology has been probably the one where most of the money has been invested, maybe because it's most compatible with current technology of big companies or fabs, etc. The advantage is it has very fast gates. It's very high gate fidelity. The disadvantage is really the infrastructure, which is huge. You need these monstrous cryogenic machines. It does not scale well because of that. You need a lot of classical cables going in and out, and this is yet an unsolved problem. And because the circuits are in the end fabricated on some substrate, which is classical, then the decoherence rate is actually quite fast. Um, so this is one technology that is being pushed by many big companies, and some people believe that it's a front runner, but it does have some challenges in the implementation. Another very important and leading technology is the trapped ion qubits. The idea is, and you see it on the left side image, is that you take ionized atoms and you trap them in very rapidly oscillating electric fields. You build a trap, it's called a Paul trap, made of these electrodes that have these oscillating fields. You can see an image here on the left bottom part, and all those blue dots are just the ions. Today, you can probably create traps holding between 50 and 100 ions. By the way, I did not say, but also in the superconducting business, this is about the range of number of qubits that has been produced, about 100. The ions here are being manipulated by lasers. So essentially, lasers are both addressing each ion and producing the gates, etc. And these experiments are also done in the end in a vacuum chamber. And these experiments, like essentially the image you see on the right are happening on an optical table and involve a lot of optics because of the fact that you are actually manipulating the ions with lasers. Photons we already described. A very important effort today is actually to do all of that on chip, on silicon. So to produce the sources, the photonic sources, the waveguides, the detectors, the nonlinear elements, everything on some wafer. And there are some big successes there. But this is the most speculative technology, I would say, because it's like you say in Hebrew, "Tzalash or tarash." I mean, it will either be super successful and then will easily scale to millions, or it will completely fail. And at the moment, it's not clear. I mean, it's already a technology that people work on for at least 10 or 15 years, and it still has a lot of challenges in it. So stay tuned. And then I'll finish by telling you a little bit about the neutral atom technology. So the idea is you take atoms and you encode the quantum information in the internal states of these atoms. And you hold these atoms in a vacuum chamber using light. We sometimes call it the optical tweezers because these traps, these optical traps, are very tightly confined laser beams that hold only a single atom there. And you can put many of these traps and you can move them around during the calculation. So you can dynamically change how the atoms are arranged. And because of that, the architecture itself is super flexible. You can take any two atoms and move them very closely to each other and implement gates by the interaction. And this is a big advantage when you come to implement quantum algorithms because you can change the geometry of the network to best fit the need of the algorithm. This is one of the state-of-the-art examples of how it is done. You can see all these green balls are depiction of atoms. And here is an example of atoms moving around. Every time you see this red circle is when you actually apply a gate. And so again, this idea that you can move the atoms around means you can implement any geometry you like. In this example, it's implementing a geometry that is equivalent to the torus. And so although these atoms are in a plane in real life, the fact you can actually move them around allow you to implement, mathematically speaking, any geometry you wish. And just to give you some numbers, the two-qubit gate fidelity today reaches 99.8%. The single qubit gate fidelity is an even order of magnitude better. So the fidelities are extremely high. The coherence times of this system are very, very long, exceeds 1 second. So these qubits can live and be coherent for very long times. And of course, it's long compared to the gate. The typical gate here is happening on a scale of, I would say, around 1 microsecond or so. Um, how do you?
Yoav, can you hear me? I will just quickly ask if it is possible to make like another few last minutes because we need to move on to the Q&A
Yes,
session.
yes, yes. Yeah, we are finishing, of course. So yeah, maybe we'll skip the preparation. It's very interesting, and we can just to say one word about how do you do gates? How do you make gates between neutral atoms? So you use something which we call Rydberg excitation, which means you take the electron and you put it in a high-lying state, and then atoms starts to talk very strongly, even when they are several microns apart. And this is how you can implement very strong interaction between atoms. And then you can implement gates. And so Rydberg gates, as I said, already reach very high fidelities today. Um, let's skip the actual example of how you do that. And this is a good slide to close to show you what is the state of the art today with this neutral atom technology. So Harvard team demonstrated already doing a logical calculation, meaning you actually use hundreds of qubits, more than 100 atoms to implement quantum error correction. So that's already very impressive, showing that you can actually reduce the error by implementing these quantum error correction algorithms. I already talked about the fidelities. Another group from Caltech demonstrated trapping of more than 6,000 qubits. So that's already super impressive. And I would say that these numbers that I just quoted are the state of the art of any technology. So neutral atom quantum computing cores are now leading in terms of what they can achieve. And this is really a very promising technology, therefore. And yeah, just last comment. Now in Israel, we established Q Factor, which is the startup I mentioned in the beginning. And it's interesting because Israel is one of only few countries that actually have companies trying to build a quantum computer in any of these modalities. And usually we see this in United States, in Europe, Germany, and China, but in smaller countries it's actually very rare, and Israel has now a representative in each technology, so I think it's an impressive. And yeah, I mean, I we leave you with this something I started with in the beginning. All these technologies that at the moment take at least a room to fill a room. It's either optical tables or cryogenics or whatever, but it's really cumbersome today. And we are talking about hundreds of qubits today, so it's almost, I would say, at the toy level. But I would urge you to be imaginative and think about what it can look in 80 years. And I'm extremely optimistic that this technology will mature and will bring a revolution to what we can do computationally speaking. And this is just the comment about the computation. I also remind you about the communication and the sensing. All of that is really showing that quantum technologies has the potential to revolutionize many of the fields we do today classically. So I stop here. Thank you very much. I hope I did not go too much over time, but if you have questions, of course, I'll be happy to take them.
Thank you very much. So I think we'll do the Q&A sessions partially from the audience here and partially from online. I see that Woody is here. Woody, will you handle the questions from them?
Yeah, sure. How do you want to start? Do you want to start with online or offline?
I think we start with the offline. We have here a microphone. 1, 2, 3. Can you hear us? Yeah, we'll start. We'll try with with the microphone, and if not, I will just forward the questions. Yeah, so anyone from the audience, or shall I start? Okay, so maybe I can do the first question. So as you mentioned, besides the mic. 1, 2, 3. Yeah. Okay. So, as you mentioned, beside being an associate professor at the Technion in the Faculty of Physics, you're also from the small company, not Factor Q. And I wanted to ask about the current challenges, maybe not all the challenges, but the main ones that you're currently facing in. Yeah.
So, yeah, I mean, the short version is that we are actually enjoying the AI boom in the sense that I think many venture capitals look for other types of investment now. Many are actually more inclined to invest in deep tech. So in a sense, this is a good time to build something which is deep tech oriented, like quantum technologies. In particular, we see a lot of interest in these fields of quantum technologies. Investors are smart. They look for only the high potential, so they want to see a mature technology, a mature team, etc. But I would say the timing is very good. And another comment is that in Israel we have kind of maybe a protection, I would say, because we are an island country. So in terms of human resource, um, we enjoy the fact that we can funnel people from almost all the country, very talented people, and we have very good people that come to work in this type of companies. So and the competition is not yet fierce. I mean, we have one company per technology, so it's still in the regime where I would say the competition is reasonable. So overall, I'm very optimistic, and I think the ecosystem in Israel is really impressive in that sense.
Okay, thank you. Yeah, maybe whoever asked the question present itself and.
Hi, Maya Anderson. Is the AI being used in developing the current quantum technologies?
Thank you. It's a great question. It's being used and heavily. I'll give two examples. One is usually when we build a quantum device, we try to build something which is called a digital twin. A digital twin is a model, essentially a physical model in software that gives us a way, at least in small systems, to predict the behavior of the actual quantum device. Building these physical models was a very heavy modeling challenge. AI has transformed it immensely. I mean, the fact that AI can build very complicated code and do that seamlessly is a huge help in this respect. Another example is, of course, in facilitating information in such companies. So sometimes you need to reach and educate and bring and consolidate information, and AI is doing that in a very efficient way. So we can use AI to scan an enormous amount of database and create a very efficient information database. And that's, again, very, very helpful in building these types of companies. So yeah, AI is used immensely. It's super important.
Thank you. Someone else from the audience?
Well, I'm thinking maybe if it's okay, I would like to suggest something because I see some questions here in the chat, but I believe that people in the audience maybe would like to mingle a little bit. So it's possible maybe to shut down the Zoom and leave it and leave you, alone to do the program. And if Professor Sagi is willing to stay in the Zoom, so people who wants to stay connected can ask questions. Is this something you find reasonable?
Hi, Rudy. I think it is possible if you continue, because we have a very good acoustics. So we in the room can stand up. We have something to drink and to eat, and we nevertheless hear your questions and we hear the answers. Is that okay?
Right. Yeah, sure. Sure. So I will handle the Q&A from the Zoom. Okay. So we'll take some maybe 2 or 3 questions and then we'll finish. So just a second. Sven is writing for a person who holds a BSc in physics, but his work experience is in software only. What skills does he need to apply work in quantum computing companies?
So I would say that we usually take more experienced people. We usually take masters and PhD. Most of the people we take are usually holding a higher degree. But if to answer the question, I would say that there are today learning path at least at the Technion, in most of the faculties, relevant faculties, that are quantum mechanical technology oriented. So you can do it in EE, you can do it in physics, and so I would say that the knowledge, probably a good combination of quantum information, that's like a course you have in most universities, at the Technion as well, and so quantum information science. There is a course I taught a couple of times, which is called the quantum technologies, and also knowledge about some of the technologies more, maybe a bit more to the depth. So this can be either courses on atom-photon interaction or on solid state. But yeah, I would say that generally only BSc is kind of hard to find a position if this is
Thank
the
you.
only.
Can I ask you a question?
Yeah, sure.
Oh, thank you. Professor Yoav, I just got a question on the other side of the quantum computers, is on the software side. Obviously, you need the algorithmic, and when we ask, what do we do with that, and what will you be doing with that? We always hear about the Shor algorithm, obviously important, but it's been written, more than 30 years ago. So is the math and the software lagging because you're going to create the machines, and it doesn't seem that anything else than the Shor algorithm has been written since?
So yeah, I have so much to say about this, but I'll keep it short. So my first comment is there were other algorithms that were published, maybe at least less famous one, but a lot of work on optimization problems, solving linear equations, for example, is something that people work on, and more. But you're completely right, and with that, I agree with you that there are certain categories of algorithms that has been developed, and it's not a general kind of a solution for any problem. And probably the quantum computer is not going to be also a solution for any problem. It's not going to replace the classical computer for sure. Having said that, I feel, and that's a speculation that I have, that we haven't even started to see the real use of the quantum computer. So in a sense, you can see it in the historical account of many revolutions. When people just do a revolution and invent new technology, usually they can't imagine what is going to be done with that. I'll give you an example is when the Wright brothers built their first plane, they probably did not have a vision of what would happen now with flight radar showing like thousands of flights in the air at the same time. And the same goes for the invention of the laser and for even for the invention of classical computing. I mean, people did not know what to do with it for a long time. And I have a feeling that this is going to be more or less the same. And by the way, it also happened with the AI. I would say that if I would tell you 5 years from back what is going now to happen, you would say I'm crazy, I'm imagining. So we have to be modest, I think, and hope that once we put this technology maturely on the table, very smart people will come up with very smart ideas of what to do with that. But I think already now there are very strong applications. But again, this is speculation. I feel like the real killer applications are not even yet invented, and that's okay. I mean, I'm okay with that.
So thank you. Baruch is writing, looking 8 years forward. Which kind of applications do you imagine as using quantum computing? Will it somehow replace binary computers, or will those technologies coexist? And another question about the future is, will quantum technology, or it's not about the future, will or is the quantum technology used in medicine? And I think this will be the last two questions. So.
Okay. So about the synergy between classical and quantum, as I said, I don't think quantum will ever, computation will ever replace classical. In fact, the perfect synergy and combination between them is actually an important question of how do you combine them smartly. And there are big challenges there. I mean, in algorithmic in classical algorithms that support the quantum calculation. For example, like decoding quantum error correction syndromes. In terms of the applications, I think probably the first layer of applications that will be enjoying this. And again, I'm kind of putting aside the cryptography, which might be the first one, but I find it less interesting, is I think really the simulating science type of applications. And then I think also the financial applications can be super beneficial. So these type of optimizations that can be done, which are very efficient and large, I have a feeling they will find application in the finance field. And about the question about the medicine, I think it will have implications there from the perspective of drugs. I mean, just finding new drugs. Today, a lot of this drug finding is done by trial and error. And some of it is because you cannot today calculate how each material will behave and have an effect. And I think um, this can be changed by if you can really calculate the full structure of molecules and understand how they work, and this can be envisioned contributing to medicine by just coming with new drugs.
Okay, so thank you so much. Thank you, our listeners from Berlin and from Israel and other countries. Thank you, Professor Sagi. Thank you so much. Bye-bye. Good night.
Bye-bye.